In this video, we're going to be talking about classification with decision trees. Now, those are terms that might be kind of new to you, but we'll start with just a general machine learning overview, and then we'll go kind of more into specifics and actually go over what we're going to be doing with decision trees, how it works, and just kind of the overall process of that decision tree making algorithm. All right, so let's get started. So as a motivation, let's look at this example problem. All right, suppose a car company wants to decide which cars to buy ad time for in the next Super Bowl. They have a data set of cars promoted in past Super Bowl ads and information about the miles per gallon, horsepower, and also they have information about which ad campaigns were successful. Right, so which cars should the company buy ad time for? Right, so basically, at its heart, this is a prediction problem. So in order to decide which cars to buy ad time for, we want to use data from previous ad campaigns to make a prediction on which cars will have successful ad campaigns. And so what we're doing is we're taking the previous information about the miles per gallon and the horsepower and whether the campaigns were successful in order to predict the future, in order to see whether the cars with certain miles per gallon and certain horsepower will have successful Super Bowl ad campaigns. So to do this, we're going to be using machine learning and more specifically using decision trees. Now, this is a subset of machine learning called supervised learning. So machine learning overall is very broad, can cover a lot of different techniques, and we're only going to be looking at this supervised learning section. And so to kind of define some of these terms, the unsupervised learning is when you have no outcome variable and are trying to create groupings based on the data. Right, so this is just looking at a large data set, or it doesn't even have to be large, but just some data set based on these different variables. You're just trying to kind of create natural groups, trying to create these clusters, and so that you can kind of describe the data better. Unsupervised learning, on the other hand, is when you have some sort of outcome variable. And many times this will be a categorical variable, and a lot of times you'll see is that you want to have this binary variable. Basically, you want to predict something like a success or a failure. And so generally what you have are the data, which consists of a lot of characteristics such as miles per gallon or the horsepower. And you also have kind of the truth about what happened in those cases, whether they were successful or not, this outcome variable. And then you use that information to see, in the future, if you have information about miles per gallon and horsepower, about these different data points, what is going to be the outcome in that case, right? When we don't have that outcome, how can we predict what that outcome is? So overall, just kind of backing up even more, machine learning is when a machine improves on a task with respect to some performance measure. And so in the case of supervised learning for Super Bowl car advertisements, we want to develop a way to improve how well we predict future successful car advertisements. Right? So we're going to improve on this task, basically determining which car advertisements are going to be successful with respect to some sort of performance measure. And we'll get to that later. But basically, this is kind of the task that we're going to do. Right? We're going to use the machine, a computer, to learn from the data in order to provide better predictions for what's going to be successful. All right, so now let's get into a little bit more about this supervised learning framework. Basically, in supervised learning, we're focused on finding the relationship between a label Y and features X. So, a lot of times you might have heard, the label Y is like the outcome variable as the dependent variable. These are all just kind of the same term, being described. Basically, a lot of different disciplines, call the same thing something different. Right? And for the features, you might have heard it called stuff like independent variable, predictors, things like that. And it's all the same. Basically, what you're doing is you're taking data from X and trying to predict Y. Right? And so this is a very simple thing that we're doing. Right? We're just trying to find this function f that kind of shows the relationship between y and x. Now, learning is finding that function f that minimizes future error in recovering y. And this future error is an important part. And we'll get to this later, but what we want to do is make sure that the future error is as little as possible, not the current error, because we do know what happened already in the present and in the past. But what we don't know is the future. We want to make sure that we're minimizing that future error. Right, so in our case, what we'll do is we'll use decision trees to find that function f that hopefully minimizes that future error when trying to determine the success of car advertisements, or y variable, based on MPG and HP, miles per gallon and horsepower, are x variables, are features. Okay, so let's say this is our data. This is our visualization of the data. We just have a scatter plot with miles per gallon on the x-axis, the horsepower on the y-axis, and we have the dots colored by whether they were successful or unsuccessful. All right, so it does look like they're pretty well separated, but we just want to be able to determine what combination of miles per gallon and horsepower best predicts successful outcomes, the successful ad campaigns. All right, so this is what we're going to do. This is just kind of a rough outline of how the tree building algorithm works. And so what it does is it considers each feature. In this case, we just have 2, horsepower and miles per gallon. Order the values in each feature. And so basically kind of like taking all of the data points and just kind of ordering it in increasing order. Right? The lowest horsepower first, highest horsepower last, and then kind of consider the split at each of those values. And then it says, oh, how well did that split do in splitting up the data set into successful and unsuccessful outcomes? How good is this at determining whether the ad campaign will be successful or unsuccessful? And basically it just considers every single split, and then it makes the split that kind of maximizes this value. There's this kind of measure of how well the split happens according to our label, and then it makes that split. So we can kind of keep on doing this with each of the 2 separate partitions that we've gotten. And then we just keep on going until we reach some sort of stopping criteria. Right, so let's kind of look visually at how this works. Right, so basically this is a tree that we built on that exact data that we showed you. Basically we have our top node, right? So this is kind of building a tree from the top and going down. What it first did is it considered all of the outcomes. And basically what you see here in this is the label on each of these little boxes is just kind of the most common category. So in this case, there were 56% successful and 44% unsuccessful. And so that's why it's labeled successful at the very top. And so that number at the very bottom, the 100% of that box, that just refers to how many data points there are in that node. And so this is just the very beginning. That number 1 box is the very beginning, and so 100% of the data points are there. And so it makes that first split, right? So the first split that it makes, the split that it determined was the best at splitting the data into unsuccessful and successful, is HP greater than or equal to 137, right? So basically, if horsepower is greater than or equal to 137, we go to yes, and there are 47% of the data there, all of which are successful. And then we look at the other side. If horsepower is less than 137, that is the no side of that branch, it goes into the next node. And so we see there it's mostly unsuccessful, 82% unsuccessful, with 53% of the data there. And so we keep on going. We split up the data even more. This time we're splitting on miles per gallon. Less than miles per gallon, less than 21 miles per gallon goes to the left. And then it goes to that node where it's about a 60-40 split in favor of unsuccessful, with 16% of the data. On the right side, if it's greater than 21 miles per gallon, it's still unsuccessful, but it looks like there's 92% unsuccessful cases in there with 38% of the data. And so it just kind of keeps on going until it gets close to these bottom 3 nodes that we see, 2, 12, and 13, where it's 100% successful, 100% successful, and 100% unsuccessful. Now, what we also see is that that last one is unsuccessful, but it's not 100% unsuccessful. it's only 92%. And this is kind of what we're talking about in terms of stopping criteria. Basically, at a certain point, we don't want to kind of keep on going because we'll create trees that are far too large. And so what we do is we say, okay, that's close enough to having, these pure nodes, having purely unsuccessful or purely successful nodes that, we'll just stop here. Right. So basically, if you look at that bottom row, that's just kind of, how we reach our conclusion. Basically, on the very left side, it's just horsepower is greater than or equal to 137. All of it goes into that bottom left node. And then the second one on the bottom row, it's, you have to have horsepower greater than or equal to 137, miles per gallon less than 21, miles per gallon greater than or equal to 20, and then it goes into that successful 100% 6% node. Right? So, this is kind of an abstract way of thinking about it, though. So let's go back to this graph that we had. We had all of the data points here with our outcome, with our features. Right? So we had the labels, successful or unsuccessful, with the features, miles per gallon, horsepower. And so what we did in that first split was basically just make this line, this dotted line that you see. And so, what we see is that, at the top, greater than that horsepower, we're going to see on all successful. And at the bottom, what we'll see is that we have a lot of unsuccessful. And so we keep on going in that tree. We keep on making splits. Right? So basically, we're going to make another split to less than 21 miles per gallon, and then another split greater than 20 miles per gallon. Right? So basically, this is kind of the visual representation of how that tree was formed. Right? What it was doing is it was making these cuts, making these partitions of the data set according to horsepower and miles per gallon. Right? So first, it made that cut, that partition, across horsepower, and then it did it across miles per gallon only within that one branch. Basically, if it was below a certain horsepower, then it made those cuts of less than 21 miles per gallon and greater than 20 miles per gallon. Right, so basically, this just kind of shows the exact same thing as the tree that I described earlier. Right, so, there's a lot of places where we may need to make decisions on building the tree. So, I talked earlier about this measure for optimal splitting. And so there's multiple ways to do this. There's something called the Gini impurity. There's also something called information gain. These work slightly differently. A lot of times they might kind of come up with the same tree, but they're just slightly different in terms of how they compute that optimal split. Basically, how well that partitioning process splits up the data set into these pure nodes. And then we have the minimum node size for stopping splits. Basically, that means that, remember when I talked about, having some sort of stopping criteria? Well, maybe, one thing that you might want to set is that, don't split once you have smaller than maybe, 5 data points within that node, because then what you're doing is you're almost starting to just kind of split the data up into individual data points, and that's not very helpful. And then you also have max depth. So basically in the tree that we saw earlier, we had a max depth of 3, or just a depth of 3. But maybe you just are interested in not going too far. If you make too many splits, then it doesn't really become very interpretable. It gets hard to understand, and that might not be desirable. And so when we're deciding these and more, there's a lot of parameters that could go into this. How should we determine what to do? How should we determine what that minimum node size should be? Things like that. And that's something that we'll go into in a later video. But basically, what we're doing here is we have this general algorithm in place, and what we want to do is make sure that all the little things that we put into that algorithm make sense.